When you are starting to use species distribution models, probably the first place to start is to use existing data which comes with the package itself. Just like the usual iris dataset, MTCAS datasets, SDM package also comes with a number of datasets which can help you to start working with it. The first thing, of course, is to install the package once you have R. So if you write install.packages and then you put SDM in quotes, you will be able to have the package. But for now, I will comment it out because I already have the package installed. If you want to install the latest version of the package, then you can use install from GitHub, which is a function from DevTools. And then you say Babak Naimi /SDM. This will also give you the same package, but in development version, which means a version that has not been pushed on CRAN and it's still under development. Other than DevTools, you can also use remotes. The same install GitHub, but then you can also use remotes package. So if you run any of these, you should be able to load, install SDM package. But now that means you should have DevTools and remotes packages separately installed. After that, you can use library or you can use require to get SDM into your R session. And mine is SDM version 1.2.56, and it loads a required package, which is Terra version that. So in species distribution modeling, we need species occurrence records and predictor variables. And I said there is data which comes with SDM. So to get this data, we can use a system.file function, and then we provide external as the path, and then species.shp. Then we say the package where it's coming from is SDM. So if we run this alone, we'll be able to see that it's taking us to the full path of where the shapefile is located for this species. So it means we can apply the vect function on that path to read the species shapefile. Then we can call this species. So we can put it to that object. So this is a presence absence data, because you can see there is 1, there is 0, and then we have the occurrence as the only column in that spat vector object. Apart from the species, we also need the predictor variables. And using the same system file, we can also navigate to the same external folder in SDM package library to access predictor variables which are supplied with the package itself. So we can use system.file, and then we go to external, and then we say package is SDM, and then that should be in quotes. So if we run this alone, it takes us up to that folder. So this is the path to the folder. Other than the path to the folder, we now need to list the files. List.files, which are in this folder. So all these are files inside this folder. but we only need the .sac files. So that temperature and we also need precipitation, and we also need elevation. So we provide the pattern. Those are the only .sc files. So if we put that, you can see now we only return those that are .asc files, which are the predictor variables we are interested in. Other than that, we need to provide another argument, which is full names is equal to true, so that we can read them. Full names equals true. Now this gives us, instead of just the names of these files, but the full path to each of those files. So that is when we can now provide the Rust function to read them. Rust function comes from Terra package, and Terra package was required. Now you can see we have 4 layers loaded. Then we can put this into an object, and we call it, say, preds. Now that we have predictors and species, we can build SDM data object. Of course, that's only possible if we have checked the CRS and all that, which I don't want to get into now. So we can call it a D object, and then we provide SDM data function from SDM package. And then we give the formula, which is occurrence as a function of everything. And then the other argument is train. We tell it train is where we have the presence absence data, which is the species object. And then the predictors we need are the preds. We will not provide independent test set. We don't have background because these are presence absence data, so we'll leave the rest unaffected. So that creates for us an object called D. Then with that D object, we can now create our model. And the model we can create using the SDM function. And again, we provide the occurrence as a function of everything. And then the data itself is from this D. So we just provide it D. And then the methods we want to use for now, I just want to use random forest only. Remember, there are so many methods, 22 of them. If you use get method names, you will know all the methods that you can use with SDM. So all the 22 of them. And which one you choose depends on a number of things, including how much you understand about each of these methods. And these methods are provided by different functions in R. So understanding of those functions is important, or those packages is important for you before you make use of each of these, as they help you even in tuning each of them. Other than this, we need to provide a replication method. For now, we'll just go with subsampling. And then what portion of this data do you want to use for testing? So we'll use 70% for training and 30% for testing. And then we want to run this maybe 10 times. There are other arguments you can provide, like setting parallel setting if you want to run it in parallel and all that. But just for a beginner, this is sufficient. If you want to provide more than one method, then you can put C function, and then you provide the other methods, say SVM. Okay, let me run the two for now. Now we have our model M running. As you can see, this red button with the stop sign. And once our model is run, it should not take long. We can print out the summary of the model, and it shows us that both RF and SVM in terms of AUC performed similarly, and even SVM performed better in terms of the true scale statistic, which is the TSS. Anyway, that's not the gist of or the main thing we are working on today. What we want to see is prediction. So our prediction, we can just use predict function. And then with this predict function, we provide our model, which is M, which we have created up here. And then the new data we are making prediction on is spreads. So we put that there. Then we can say mean is equal to true, so that each of these, we have a mean for the random forest and a mean for the support vector machine produced. Otherwise, we would be having 10 of random forest predictions and 10 of support vector machine predictions. We only want the mean of this and the mean of this separately, not the mean of both of them. So that's what mean equals true is helping us to get there. So if we look at P, it should be a sparse raster object. Sorry, that's capital P. It should be a sparse raster object with 2 layers. It's 2 layers because we have prediction for random forest and we have prediction for support vector machine. Okay, so we are almost done, because now what we can do is just to plot P to visualize the predictions of our species, of our models, how each model predicted the potential suitable habitat of this species of interest. And yeah, based on this, we can pick which one we want to share with our stakeholders, or we want to use for our publications or something. But again, I'm keeping this super simple because it's a super basic introduction into species distribution modeling. The workflow here is simple. We load the library. Of course, we install it if we don't have it. My version here is 1.2.56. We load the species data, which is inbuilt or which comes with the package. Then we load the predictor variables, which come with the package. We create SDMD object. Then we build the model and make prediction. A lot of things have not been put into consideration, like we've not chose our replication method based on anything like bootstrapping or cross-validation and the k-folds provided. Our methods here, we've just chose them randomly, random forest and support vector machine. There's several others, BRT, GLM, FDA, and 22 others or 20 others. And then our predictor variables, we just pick 4 randomly. We didn't even check for the multicollinearity and everything. So I'm aware of most of other things that should be done that we have not done. But for someone who is just making the first step into species distribution modeling, I think running this and seeing an output is more than sufficient. Well, if you want to see some nice plots for your predictor variables like R curve, how the response curve look like based on the response and the predictor variables you chose. You can use R curve function. And then if you want to see the rock of the same M, we can do that. Response curve looks like this. Not so good for elevation, but at least the rest are unimodal, like almost one mod. one peak. The rock is about the sensitivity and specificity. Yeah, we expect this blue line to come as close as possible to 1. I'm just going fast over them, but another graphical user interface which is important for some of us is this, where you see all the, for example, random forest was run 10 times, and then support vector machine was also run 10 times. And we can see a lot of evaluation metrics, both threshold based, the sensitivity, and all these, which I don't want to get into. But if you use GUI M, you can see all that. All right, so what next? Normally, after building your model and you close your machine, your model will disappear. So when you restart your R, you will have to build another model. But because of this function write SDM, you can put the model you've trained and then save it to your working directory as sdm.sdm, or you can put it mysdm or whichever name you want, provided you are within your working directory, then it will be saved there. And if you will want to use it when you come back, you now don't need to run all this. You just start from here and say read SDM, and then you provide the mysdm, the path to mysdm .sdm, and then it will load this as M. You will read it like that, and then you can use it. The exact model you trained, you can use it down to make predictions, to do other things. And you can even send this file from your working directory. You can send it to your colleagues to make predictions with it wherever they are. And same to the output of predict, like P here. You can use write raster to save it. For example, write raster P, and then you provide the path to where this raster is supposed to be. Maybe you want to call it my raster.tif, and then it will be written as a TIFF file in your path, whichever path you have. Can be D something, D:/ blah, 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 up to your folder. That is if you're not working in a project. But if you're working in a project, then that should be straightforward. Okay, so that's all I wanted to share for today. Thank you for your attention. And I will push this script to my GitHub repository, and I will provide link to that. Thank you.